lines in 2D and 3D. So this lesson we're talking about how to write vector equations of lines in both 2D and 3D. And this is what we consider a vector equation. R equals A plus TB. So how's this a vector equation? How do we use it, I should say? Well, here's A is our fixed point. So we need a point to write a vector equation. So this is our fixed point. I sometimes like to say the starting point, but this has to be any fixed point. And then what's also important is that B here is our direction vector. Super important. So let's know which direction or what angle your vector is going at. So direction, the angle, vector is going at. And T is a variable. So in vector equations, we write T as a variable. So we have our fixed point, we have the direction vector, and then we have our T. And that comes up and that's a vector equation. So here's a line in 2D, and you can see here, let's say we start at A, look, you see the arrow is starting at A and going toward R. So we start our fixed point, A1, A2, and we're going in the direction of this vector here, B1, B2. So it's written like this. That'll be a vector equation on that side. If you want to find the slope of the line, keep in mind, so if you ever asked about the slope or gradient of a line, right? Slope is, when you do think of slope, you think of change in y over change of x. And that's still true for vectors. But if you think about a vector equation like b1, b2, the top one is the x and the bottom one is the y. So it's a little weird. When you want to find the slope of a vector line, you use that direction, but you got to flip it, right? Slope is y over x, so it's actually b2 over b1. So you still write the same. Like my vector equation does not change, but when you do slope, you're like, yeah, remember, it's y over x. So it'll be the y value of the b over the x value of the b. And I don't care about a at all, because a is the point. It's all about the direction vector. You can also write this vector equation in a different form, a form we call the parametric equations. So that's where you just add up across. So x value plus x value, y value plus y value. You can get this right here. X equals a1 plus b2. This is called a parametric equation. So it's like your normal xy equation, but you have an extra variable. So you're going to have x, y, and a t. So when you separate them out, we call those t is our parameter, and we call it a parametric equation. And we also have a Cartesian equation. That's the one you're more used to. A Cartesian equation is just a normal x plus y equation. That's considered a Cartesian equation. So we just eliminate the t to find it. And we'll go through an example of how to turn a parametric equation into a Cartesian equation. It's not that bad. So let's do some examples. So they want to find a line that passes through A and has a direction vector 3, 2, described using a vector equation, a parametric equation, and a Cartesian equation. Okay, so let's talk about a vector equation. That's actually a form on your former sheet, and that is the thing we saw earlier. R equals A plus TB. Keep in mind, A is the initial point, and B is the direction vector. T is just a parameter. So if I was doing a vector equation, it would be xy equals my initial point A, 1, 5, right? 1's the x, 5 is the y, plus some variable t times the direction vector, which in this case, they tell us is 3, 2. And that is it. That's it for my vector equation. You're done. If you want to do a parametric equation, super simple. You just separate it all. Separate the x's, x equals 1 plus 3t, and separate the y's, y plus 5 plus 2t. So x would equal 1 plus 3t, and y would equal 5 plus 2t. If you want, you can rewrite it, but that's the general idea. So there's your parametric equation. Super simple to separate them. Done. Now to find a Cartesian equation, you have to turn this into a Cartesian equation. It's not the worst thing in the world, but it's not as simple as those two. All we have to do is eliminate x. Eliminate the t. So how do you do that? Well, all we're going to do is solve for t and plug into the other one. So it doesn't really matter to me ugly either way. Let's solve for t here. All right, so I'll get x minus 1 equals 3t. Divide by 3. So x minus 1 over 3 equals t. So I found out what my t equals, and I'm going to plug it into the t for this equation. So I'm going to get something else like this. Y equals 5 plus 2 times x minus 1 over 3. If I want to simplify that a little bit, I mean, it's already a parametric equation, but I could simplify it a bit. I get something like that. And if I want, I could even do more with that. 2x over 3 minus 6 over 3, which is just saying 2 to 6, not a b, to 6, not an ugly b, to 6. That's a mess. Yeah, I could just do that. There's a 6. So then you can add up to 5 and 2, and you get 5 minus 2, and you get y equals 3 plus 2x over 3. That's a Cartesian equation. Right, so you just eliminate the t, solve for what t, plug into the other equation, and then you solve, and that's a Cartesian equation. So hopefully super simple. Right, vector equation, just initial point and then direction. And then for parametric, you just separate them, and then for Cartesian, you get solve for t, plug into the other equation. Lines in 3D work about the same. We just add an extra. We have the z line. Everything else stays the same. So the line in 3D, b is a direction vector still. If you want to do a parametric equation, you just separate them all. So it works the same way. A little note here: in 3D, you don't actually have a slope, so we don't call gradient a slope of a line. We'll just say the direction of the vector. So let's find a vector equation and the corresponding parametric equation of the line through -1, 2, 3 in the direction of 4i, 5j, minus 6k. So this is our initial point. Well, first let's put the formula down, right? So the general formula is r equals a plus tb. This is the initial point, and then this is the direction vector. So remember, that's that's the unit vector notation of it. We're gonna rewrite it in a second. So we're gonna say x, y, z equals initial point 1, -2, 3 plus t times my direction vector, so 4, 5, -6. So that's a vector equation. If you want an parametric equation, you just separate it all. X equals 1 plus 4t, y equals -2 plus 5t, and z equals 3 minus 6t. And there we go. Non-uniqueness of a vector equation of a line. So what all this means is that there's lots of ways to write a line. So remember when you write a vector equation, it's r equals the initial point or a point plus the direction vector. The direction vector is actually the most important part. That lets you know what the slope is, which way you're going. The initial point could be anything. So if for example here, if you start at 5, 4, it's your first initial point. As long as your direction vector is 2, -1, that's the same line as starting at 7, 3 and going on that line. So there's lots of ways to write a vector notation, the vector equation. The most important part of the vector equation is the direction vector. As long as that's true, you could use any point on that line to find one. That's all this is saying here. So let's do this quick example. Find a parametric equation of the line through A and B. So our formula is, as we always have, plus TB. Remember, this is in the formula sheet. So here you could go any way you want to start. Do you want to go line AB? Or do you want to draw a line BA? Both are equal. I mean, they're going to be slightly different answers, but they're both going to be true. So do you want to start A, go toward B, or do you want to start B and go toward A? I generally do AB, but it does not matter. So let's say I'm starting at A, which is this point, and I'm going toward B, which is this point. Now, remember, we're doing our initial point AB. So why does it matter if I go AB or BA? Well, because of this right here. So my initial point is A in this case. So this will be point A. Now, here's the most common mistake people make. They just think, oh, I'll put B as my direction vector. That's not it. The direction vector is which direction you're going. B is another point. So the direction vector is a vector. This is actually AB. Remember how we find AB? Tip minus tail, B minus A. So anytime you do this, this has to be that point there. So it's not just the point, it's the vector AB. So if I'm starting at A, I'm going toward B, so I got to find the vector here, AB. So vector AB, which would be B minus A, would be -1, 0, 2 minus 2, -1, 4, also known as -3, 1, and -2. So my equation is going to be this: x, y, z equals -0.2, -1, 4, plus t times my direction vector, -3, 1, -2. So again, cannot stress enough, very important. Your direction vector is not this other point; it's the vector. So you gotta find like a vector. In this case, AB. If I did the opposite way, and if I want to do parametric, I just separate them all. If I want to do the opposite way, BA. Well, now your initial point would be B. So I'll just put R equals my B, -1, 0, 2, plus the direction vector. Now remember, your direction vector is not just A, it's the vector BA. So this would be tip minus tail. So in this case, that would be 2, -1, 4 minus -1, 0, 2, which would get me 3, -1, and 2. Now again, these are actually the exact same line. You might look at it like that way. They start at different points and they have different direction vectors. Their actual direction vectors are not actually that much different. They're parallel to each other, if you notice. This is -3, 1, -2. This is 3, -1, 2. If you multiply this direction vector by -1, you get this direction vector. They're actually parallel. And when you're parallel, you're going the same direction. just opposite sides. So you can write either way, and both ways are true. And that's the vid.